Hello everyone. Let's continue and look into the concept of registers. So we need to answer a query where we mentioned that there are only 32 registers available in the RISC-V architecture. We need to understand why are there only 32 registers. So let's look into the concept of registers through an example. So what we'll do is now let's consider the XLN as 64-bit because all the concepts and all the examples that we are taking, that is for a RISC-V 64-bit architecture. So let's assume that the XLN is 64-bit, which means all the registers are 64-bit and the length of it's basically the bit number starts from 0 and ends at 63. So let's talk about a 64-bit example over here. So if you look over here, this particular number, this is one of the numbers that we have discussed in the past couple of videos while discussing about the signed and the unsigned numbers. So this is a positive number because the MSB is 0, so this is a positive 64-bit number, and the way this number can be loaded in any of the registers or any of the 64-bit registers will come back to the count of the registers. But right now let's say there are X number of registers, and if you want to load this number in any 64-bit registers, there are two ways to do it. There are primarily two ways to do it. First of all, you can load it in you can load it directly, that this numbers can be directly settled in this particular registers. But since there are only few limited number of registers, it can hold only minimum amount of data, but the major amount of data can be stored in a memory. Either you can store this particular data in the memory, and from the memory it can be loaded to the register. So there are two different ways to load the data in the register. So registers can be available, or the data, the 64-bit data can be directly available inside the registers, or they can be loaded from the memory. Now there are different ways to load this particular thing from the memory. First of all, we need to look how these particular things are being arranged inside the memory, because memory addresses a byte. For example, each memory address will address a single byte. If let's say the address of this one, this particular address was M of 0, M of 1, M of 2. So M of 0 will address the address M of 0 will load a single byte. M of 1 will load a single byte, and so on. But over here we have a 64-bit data. How does this thing gets accommodated over here? The way it does it is the lowest LSB is least significant byte. Now in this case, the lowest significant byte goes and sits over here. If you see this, for the below 8 bits, or the first byte or the lowest byte goes and comes and sits over here. The next byte, starting from this point till this point, that comes and sits over here in the second line. The next byte from this point and the next byte, or maybe the next 8 bits from this point, starting from this point, goes and sits over here. Okay, over at this address of the memory. The next 8 bits comes and sits over here. Okay, this thing sits over here. The next 8 bits starting from this point to this point sits at this point of the memory. The next 8 bits from this point till this point, they come and sit at this point, at this portion of the memory. The next 8 bits sit over here, and the final 8 bits comes and sits over here. So this is basically this is the structure of the memory. And if you see over here, the lowest bytes, in this case, the MSB we have defined as most significant. This is the most significant bit, and this is the most significant byte. So your most significant byte comes at this point, and your least significant byte comes at this point. So this structure of the memory, or this structure of the memory system, is referred to as Little Indian Memory Addressing System. So RISC-V belongs to this particular category. There is another memory addressing system which is called as the Big Indian Memory Addressing System. In that case, the most significant byte comes and sits over here. This one sits over here, and accordingly this one sits over here. That's called the reverse of the Little Indian, which is nothing but the Big Indian Memory Addressing System. In this case, we're looking into the Little Indian Memory Addressing System because that's what RISC-V architecture is about. So this is a part of the RISC-V ISS specification. So RISC-V belongs to the Little Indian Memory Addressing System. Now, if you look into the addressing of this one, for example, this M of 0 will hold 1 byte, M of 1 will hold 1 byte, M of 2 will hold another byte, and so on. So address of one single double word. So this thing, the address of this entire double word will be M of 0. The address of the next double word that will load will be M of 8, and so on. So it's a multiple of 8. For example, now let's try to conclude something. If the address of the first double word is M of 0, then the address of the next double word is M of 8, address of the third double word is M of 16, and so on. So what we'll do is, let's take an example of this one. If you look at an example, let's say we'll take an example of an array which holds 3 double words. So 3 double words, which means from 0 to 7. 8 to 15 and 16 to 23. So it holds 3 double words. Now for example, let's say M of 16 holds the lowest significant bytes and M of 23 holds the most significant bytes. In that case, how are we going to load this particular data in the registers? So what we'll do is that will need us to understand some few of the basic a few of the basic RISC-V ISA commands. Basically we are now entering into the actual specification, actual commands or actual instructions that will be needed to load this particular data inside the register. So what we'll do is we'll stop at this point and look into the exact command that will help us to load this data inside this 64-bit registers, and hence we are also going to look into why do we need 32 registers in the RISC-V architecture. So let's stop at this point and let's look into all this from the next video. Thank you.